property of linear maps. This is sort of the extra property. Linear maps. First of all, these are maps between vector spaces. Now, so that a vector space has an unlimited number of vectors in it. So these pictures, they don't like these pictures that we've defined for these properties, but the maps they still have to be well defined, and they still have to, the properties of one-to-one and onto mean the same thing. And here, while you can't draw the diagrams, these logical definitions still hold true. So we can still deal with these A1 and A2s and Bs will all be vectors instead of just numbers or simple elements. Okay, so they're maps between vector spaces. That's the maps part. But what about the linear part? Well, the linear part, and we'll always be interested only in linear maps. Linear maps preserve linear combinations. So they map all linear combinations in one space into linear combinations in the other space. So if I have, so I still have, let's say I have a domain V, and I have a codomain W, and say I have a map F. And so let's say I might have two vectors here, V1 and V2. Now, so these vectors are going to have, because they're members of the domain, to be well defined, there have to be elements W1, which equals the image of V1, and W2, which equals the image of V2. In other words, to be well defined, this map, there has to be an image of every domain element. Now, that just says it's a map. Now, to be linear, here's the linear property, which is going to be sort of a crucial thing, is that given any linear combination in V, we have to, the map, there's a property. Now, to have any linear combination of V, we can, to get that, we can choose any numbers, say R and S in our number, and then we can say, okay, if this V1 and V2 are arbitrary, then we have not A, but say we have R V1 plus S V2. So this is an arbitrary linear combination of two vectors, okay? So if I take any number times V1 plus any number times V2, and V1 and V2 can be any vectors in the domain. Well, so this is I've chosen, this is an arbitrary linear combination. So the map F here is linear. F is linear if the following property holds. Is true. That F of, since this is a vector space, this is a member of the domain, so it has to have an image under F. So we have the image of this vector is linear if this following holds true: R times F of V1 plus S times F of V2. So this is saying the image of a linear combination is the same linear combination, that is the same R and S, with the images of V1 and V2. So the image of a linear combination is the same linear combination of the images. So that's sort of to say it in words, the image of any linear combination is the same linear combination of the images. Now let's see, we should, now it's important now to go and actually be concrete here and do some examples. So because this is the first one where we're first property, let's get down, let's see. Let me find some, yeah, here's the definition, a linear map. Here's there's a slightly different property. You'll see that this definition is the same as this one here, but this one sort of captures the spirit of what's going on. And let us find I'm sort of going to the second part of this first. I want to find some, okay. Well, let me just instead of going through there, we'll pick up with a text since it's okay. Okay, so here's how to how would I define a map? How would I give or how to present to you a map? Let's say I wanted to have a map from R to C, or let's do it R3C to R2C. Let's say we have the map F from, so what we have to do is we have to say, okay, we have to take any element of R3C. So we have to have any element here. So X, Y, and Z can be any numbers. And we say this has to go to, under F, some element here of R2. So it's going to have two components. So it could be sort of, for example, X plus Y and Y plus Z. Okay. So here's a map. It says for anyone here, we can show it's a map. And the question is, I'm telling you it's a map. We could verify that explicitly, but the question is this map linear? Now, it's going to turn out that if the components of the vector over here are linear combinations of the components over here, it will be linear. But let's see how that works out, right? Let's say that I wanted to check that property. What would it mean? It would mean that if I had, for example, say, let's look at what's the image of 1, 2, 3. Let's say V1 is 1, 2, 3. So what is F of V1? F of V1 would equal, well, this is X, Y, and Z. So X plus Y is 1 plus 2 is 3. And Y plus Z would be 2 plus 3 is 5. So there's the image of V1. Okay, does you guys see that? And what's the image now of V2? Let's choose another one, say 4, 5, 6. Then what is the image of V2? Well, that would have to be X plus 4 plus 5 is 9. And then Y plus Z would be 5 plus 6 is 11. So this is the image of V2. Now, the claim is that what's the image? Let's say I take a linear combination. Let's say I take 3 times V1 or let's say I take, 3 plus 1, 2 times V2, and I ask, what's the image of this? Okay. Well, what I have to do is all I have is this rule here. So what I have to do is I have to find out what vector this is in terms of x, y, z, then apply that rule. So this is going to be f, the image of 3 times v1, which is 1, 2, 3, plus 2 times 4, 5, 6. Okay, so that's going to be the image of multiplying the 3 in, 3, 6, 9, plus 8, 10, 12, which equals the image. We have to then put these together. 8 plus 3 is 11, 10 plus 6 is 16, 9 plus 12 looks like 21. Okay, well, so here now we have a form, because we sort of combined, we found out what the particular vector in R3 is, that's defined by this linear combination here, and then we can apply the rule, because then we know that this is x plus y is 27, and then y plus z is 37. So that's the image. So now the claim is that this, if it's linear in this case, it should be equal to 3 times f of v1 plus 2 times f of v2. That's the linear property, right? Here. So we can try, then we can sort of see, well, we can actually calculate this directly and say this is 3 times, what's the image of v1? v1 was 3, 5. What's the image of v2? v2 was 9 and 11. Okay, well, we can then calculate this. 3 times 3 is 9, 3 5s is 15, 2 9s is 18, and 2 11s is 22. And then we can, 9 plus 18 is 27, and 15 plus 22 is 37. And it turns out that that's the same as this one. So that's an example. This is an example of linearity, of a linear map, of a linear map action. The issue is, though, I might want to know. So the problem is this: I did this with specific vectors, but the problem is, for the map to be linear, this has to hold true for every single linear combination I choose here. So v1 has to be any vector, v2 has to be any vector, r has to be, this number 3 has to be replaced by any number, this vector 2 has to be replaced by any number. So if you wanted to show, and that's one of the things that that you want to be able to do, is and it's a little bit unwieldy, because you're choosing, you have to choose arbitrary linear combinations. So if I choose an arbitrary linear combination, I have to choose v1 for the same map x1, x2, x. No, that wouldn't be quite right. I have x, y, and z. x1, y1, z1, and v2 would have to be x2, y2, z2. So you see here I've got two vectors. Since I'm going to choose x1, y1, and z1, choose x2, y2, z2. Then I have two vectors. Then I'm going to choose two numbers, r and s, real numbers. And then I want to do f. I'm doing the same thing I did before. R times v1 plus s times v2. And that's going to be the same as f of r times v1, which is going to be r x1, r y1, r z1, plus s times v2, which is s x2, s y2 s z2, and then that's going to be the image of where I have to add those two together, and I'll get rx1 plus sx2 ry1 plus sy2 and rz1 plus sz2. So I've done the same calculation I just did with numbers, but with these letters to represent, I'm doing it for arbitrary case. Now, once I have it in this form, I have three components, and I can find the image here, because the image of this is the two component vector where the numerator is the sum of these two, rx1 plus sx2 plus ry1 plus sy2. So I've added the first row and the second row, and the next one is the sum of the second row and the third row. So I can do ry1 plus sy2 plus rz1 plus sz2. Now, the question is this equal to the image of r times the image of v1 plus s times the image of v2? Well, one thing is we could try to just massage or change this vector, so to speak, by doing some little algebra. The idea then is, what we want to do is we want to see, we've got a 1 and a 2 and a 1 and a 2. The idea is to move all the 1s on the left and all the 2s on the right. So I'm going to have rx1 plus ry1, right? That's the first and the third term, plus sx2 plus sy2. So I've got the 1s over here. Then I can do the same thing here, ry1 plus rz1 plus sy2 plus sz2. So I just reordered them using commutativity to move all the 1s on the left. But now you can see this is sort of like I can then decompose on this sum here, as this is going to be the sum of rx1 plus ry1 plus rz1 plus sx2 plus sy2 plus sz2. It's a little tedious, but so it's like something you don't want to do too many times, but you need to understand the process. Now, so I've decomposed this sum into the two vectors. You can check it by just seeing that if I add these back, I get this top here. Now you can see that I can factor by the distributive property of arithmetic. I could factor the r out here, the r out here, and then the r would then be able to be factored out of the vector. So I'm going to be able to get r times x1 plus y1 plus z1, and do the same over here, factor out the s, and I get x2 plus y2 plus y2 plus z2. And if you notice now that the image of x1, y1, z1 equals x1 plus y1, y1 plus z1, and the image of x2, y2, z2 equals the sum of the first two, x2 plus y2, then y2 plus z2. So you can see here, this vector here is the same as this. This is r times f, and this is v1, f of v1 plus s times f of v2. So this verifies. And I could have just started from this, used these definitions and gone to the middle and showed they're both equal to the same thing. But this verifies that this map is linear. Okay, so that's this is a an example of verifying that a map is linear. Now, there's also a rule of thumb. The rule of thumb is in one of these maps that's given here, let's see where the definition of F is. Where did I give? Okay, here. Yes. No, it must be way up at the top. Okay. Where did I define F? Oh, here it is here. The rule of thumb is if the linear combinations, if the components of the image vector here are linear combinations of the components over here, then it's going to be linear. And okay, so that's the idea of linearity. And what we're mainly going to be interested is using these maps, not just verifying that they're linear, but you need to understand the linear property and how that works. And there is, see, here's linear maps. And what I do, there's some definitions where this is repeated. And then I give you various examples here, and you're supposed to identify which of these maps are linear. And there's another linear map, a third linear map. Then we're going to go on and now do properties of linear maps, and then we'll have more stuff about that. But okay, so we have basically this verifies that it's a linear map, but the question is, now we want to be able to look at the properties. Now we have to do the properties of linear maps. And this is a good break point. So let me